Welcome everyone to the Physics Colloquium. Today we have Professor Anna Watts visiting us virtually. Professor Watts is an expert in neutron stars and particularly studying what's in the core of a neutron star with very novel astrophysical observations. Professor Watts got her PhD in mathematics at the University of Southampton, then went on to a research associate position at NASA Goddard, to a postdoctoral fellow in Garching at the Max Planck Institute, before she went to Amsterdam, where she is now a full professor. And it's my pleasure to announce Professor Watts. So please go ahead and tell us about neutron stars.
Well, thank you very much. And also thank you very much for the possibility to give this talk remotely. Unfortunately, I'm not able to travel at the moment, so I'm very, very grateful for that. So I'm going to talk today about mapping neutron stars inside and out. And I'm going to talk about X-ray data coming from a telescope on the space station, which is why I have the space station behind me as well. And I will also come back onto that. But let me start off by telling you essentially why we should be interested in mapping neutron stars for start on the inside. And this is really kind of the physics pitch. So neutron stars are the compact remnants that result after the supernova at the end of the life of massive stars that are not quite massive enough to collapse to form a black hole. But essentially you get a mid-range where you will form instead a neutron star as the compact remnant. Neutron stars are incredibly dense. You have maybe one, perhaps up to 2.5, 3 solar masses of material crammed into a sphere somewhere between maybe 18 up to about 30 kilometers across in diameter. And that means we have material of supranuclear densities. What you're seeing here is our kind of basic idea of what a neutron star looks like on the inside, basically from theory. We think, a solid crust, basically on the neutron star, and that will be a lattice of ions. Those ions will get progressively more and more neutron-rich as you go deeper into the crust. At some point, essentially, you will reach the point essentially where the nuclei are becoming more and more neutron-rich, basically as you get more and more dense, and neutrons will start to drip out of the crustal nuclei. So I now have a crustal lattice. I have electrons, degenerate electrons there, and I also now have free neutrons, most likely in a superfluid state. And that is a whole other talk about superfluidity. I continue going deeper and deeper, basically into the solid crust. The nuclei become more and more neutron-rich still, more and more free neutrons, and eventually they will start to merge into each other at the base of the crust. And that is where we come into what we know as the core. Now, the composition of the core is really quite unknown at the present time. It could well be that the core of the neutron star is indeed mostly neutrons. But even then, it wouldn't be 100% neutrons. You'd have maybe 95% neutrons, protons, muons, and electrons in the mix as well, a kind of supranuclear density fluid with high neutron-proton ratio. But there are many more interesting possibilities as well. One is that within the core of the star, you have time for weak interactions to operate to form stable states of strange matter. So inside the cores of neutron stars, you may find strange quarks in the form of particles, in hyperons, for example. You may also find deconfined quark material, up-down strange quark mixtures, forming perhaps deep in the core of the star as well. So there are lots of creative and interesting dense matter possibilities that we may find in the cores of neutron stars, with densities getting up to several times the density of a regular atomic nucleus. So these are the kind of theoretical possibilities for what we might see. Now, to put that in a wider context, this means that in principle, we can use neutron stars to try to understand strong force physics. And here we form part of a much, much wider community. What I'm showing you here is my incredibly simplified phase diagram of the whole universe. What you see here on the y-axis is temperature, and on the x-axis, chemical potential, although if you prefer, you can think of this kind of as density. Astronomers tend to prefer to think of it in terms of density. We live, basically everything around you, basically in the room that you're sitting in, down in this lower left-hand portion, the region of regular hadrons and regular nuclei, low temperature and relatively low regular atomic nucleus density. We would like to understand what happens as we go to extremes of temperature and density. Now, in principle, we have a theory that should describe this, quantum chromodynamics, but it is extremely difficult to carry out first principles calculations, basically to predict the properties, even of relatively simple atomic nuclei. It's very, very computationally challenging. So what we tend to do instead is we basically make, or my theoretical physics colleagues, make phenomenological models, basically of interactions that we can then test against experiment and observation. Now, basically, astrophysicists are not the only people getting in on this game. You can do this, of course, in the laboratory. And we have colleagues working on heavy ion collision experiments all around the world who are exploring this kind of region up towards here, this kind of high temperature, low to intermediate density region, wanting to understand, what happens as you go to these extremes. Are you forming, for example, quark-gluon plasmas? Neutron stars basically occupy this region down in the lower right-hand portion of the diagram. So lower temperature, but in principle, potentially higher density. And if you're interested in the mergers of neutron stars, perhaps the gravitational wave signals that come from them, you're a little bit perhaps more towards the higher temperature region because thermal effects then become important. And also if you're studying newborn neutron stars as well. But essentially across this collective of experiment to observation, we are studying these very different regions. Now, neutron stars essentially probe this unique range of parameter space, essentially down at low temperature and very, very high density. Said you can get to a few times nuclear density, highly neutron-rich states of matter, and the only possibility in the universe of forming stable states of strange matter. So they are unique places to do nuclear physics, but ultimately we also have to connect in this wider picture to the results coming from heavy ion collision experiments. So that, if you like, is the nuclear physics motivation for wanting to study neutron stars because they give us this unique part of parameter space. So how do we, as astronomers, produce something that can actually connect back to this nuclear physics picture? Well, the entire chain of logic that we follow is summarized in this diagram here. What we've talked about so far is the stuff in the bottom left. So the uncertainties, for example, in the types of particles, the core composition that you find in this supranuclear density environment. Are we just dealing, for example, with nucleonic matter, mostly neutrons with some protons? Again, very hard to test in the laboratory. Could we be dealing with hyperons, perhaps 10% hyperons in the core of the star? Are we dealing with deconfined quark matter? Now, the forces between the particles and the types of particles that are there on the microscopic level set on the macroscopic level the equation of state. And that is essentially the relationship between pressure and density. Now, I should perhaps be showing you temperature on here as well. And if you were studying neutron star mergers, you would need to consider temperature in here too. Fortunately, I'm going to talk about mostly old and cold neutron stars, so I don't have to worry about temperature effects on my equation of state. But in principle, all of these different compositions and different force descriptions form different predictions for the equation of state. And this blue band is a parameterized family of models that spreads over this wide range. I still need to connect to stellar properties. Now, fortunately, the equation of state is an ingredient that goes into the stellar structure equations when you want to build a model of a star. For neutron stars, they are high-density objects, so they're relativistic. So you need to solve the relativistic stellar structure equations, the Tolman-Oppenheimer-Volkov equations. You basically pick a central density, you integrate out your stellar structure equations, basically mass conservation, force balance, with your equation of state, come towards your edge of your star, however you choose to define that. And at that point, you have a mass and a radius for your star. You then tweak central density, repeat the calculation, and eventually you will trace out for each equation of state, you will trace out a mass-radius relationship. And that is what you are seeing here, basically in this right-hand panel. So in principle, every equation of state has an associated mass-radius relation. And again, this pale blue band is a parameterized family of models that spread essentially across this whole wide range. So in principle, if we can measure the mass-radius relationship really well, we can get to the equation of state. So how do we do that? Well, now we take advantage of relativity, because the mass and the radius, basically together with the spin of the star, which can be extremely fast, basically those together set the space-time of the neutron star. And again, it's a relativistic space-time. So it can be distorted, and that's something we take advantage of. So basically, any photon that leaves the surface of the neutron star propagates out through this space-time. It can pick up the imprint of things that depend on the mass and the radius, and we can actually model that. From this, we can measure mass and radius. We try to do this for multiple stars. That gives us essentially something we can fold back through the stellar structure equations to get the equation of state. And then I can hand that to my nuclear physics colleagues, and they can tell me essentially what it all means. So that is the logic that we follow. So let me now introduce you basically to the NICER telescope, which is our primary way of doing this so far. NICER is the Neutron Star Interior Composition Explorer. It is an X-ray telescope, and you can get a feel for the size here. That's installed on the International Space Station. This is one of my all-time favorite photographs of NICER, because when it was first launched, my children were massive fans of Ninjago and thought I was working with a team of ninjas. They now sadly know better. It was launched in 2017, went up on a Falcon 9, and installed, basically pulled out and installed on the International Space Station. So if we come to the picture of the International Space Station, this is where NICER sits. If anyone has the Lego model of the International Space Station, NICER is not on the standard model, but you can make your own mini NICER, and I have done this to stick on your Lego Space Station model. So it is there. The other rather lovely thing about having a telescope on the space station is you don't just wave it goodbye, as you would with a normal X-ray telescope, where you send it off and you never see it again. On the ISS, there are cameras, and so you can actually take movies of NICER. And this is a movie very much sped up, showing you how it operates. Those are the detectors. Basically in there, we have an X-ray concentrator array onto silicon drift detectors to record X-ray photons. You can also see the rather complex environment that NICER is operating in. We've got solar panels swinging around, but the advantage of being on the space station is a lot to do with cost. We take advantage of obviously the power, data transmission, and so on, being on the space station. And the other rather nice thing is that if there is a problem with NICER, you can actually go out and get it repaired. And in fact, there is a repair mission currently planned. NICER actually has some small holes in it right now, basically in some of the shielding. And there is a patch kit now on the space station, which will be installed basically in a spacewalk shortly to actually try and sort out the small damage that's been done to the telescope. So one nice advantage of being on the space station. So let's talk a little bit more about the kind of technique that NICER is using. So I mentioned we were using essentially relativity as a tool. And in fact, the technique that we use is called pulse profile modeling, because we don't just pick any old neutron star. We pick very specific neutron stars where the X-ray emission that comes from the surface is not uniform. And so this means essentially that as the star rotates, the emission varies. And what you can see in the movie here is effectively an example of one of the type of effects that we're using. So on the left-hand side, basically, this is a standard Newtonian gravity star. It has a hot spot emitting X-rays on the surface. As the spot turns around, the spot goes out of sight, and we see the emission drop to zero. On the right-hand side, basically, you see essentially the effects of gravitational lensing. So now, basically, because of light bending, we're seeing some of the back of the star as well. And so now in this geometry, as the spot goes around the back of the star, we don't lose it. We actually still see some emission from it. And this is just one of the relativistic effects that we take advantage of, because we understand, thanks to a lot of work by a lot of smart people, very well how to model emission through the relativistic spacetimes of neutron stars, taking into account their spin, the fact that they're ablate in shape, they're not entirely spherical due to the rotation as well. And so if we put a hotspot on the surface for a given mass, radius, and spin, we can predict very well what that emission should look like. So we have a good way of modeling things. The type of neutron stars that NICER is primarily focused on to date are rotation-powered millisecond X-ray pulsars. So that's a specific type of neutron star. Basically, they are X-ray pulsars. They have an X-ray spot, so as the star rotates, it pulses due to the rotation. Basically, the hot spots are coming from magnetospheric return currents. Neutron stars have very, very strong magnetic fields, although these are some of the weaker ones for neutron stars, perhaps essentially under 10 to the 7 Gauss. But we still have currents flowing in the magnetic field. Basically, these return currents are then heating the magnetic poles of the star to temperatures where they emit in the X-ray. There are other types of X-ray pulses that I'll talk about later, which come from different mechanism. But essentially, these ones, it's literally just current flowing as the star rotates. And in principle, here we have a simple dipole magnetic field. Basically, I would have hot spots at the 2 magnetic poles. So these emit in the X-ray, we see thermal emission, and these are the type of stars that we're looking at. So let me now come on to the details, essentially, of the modeling process, because it has a lot of different ingredients, and it's useful to understand where those all come from. So the first thing that we have, basically, I guess one of the most important facts is the data. NICER is specifically designed to permit this kind of modeling. And so what we have is incredibly good energy resolution and incredibly good time resolution. These neutron stars are spinning several hundred times a second, so extremely, extremely fast. And what we want to build up is a very, very good time resolved picture of how they behave, because we're going to take advantage of those rotational effects, which are linked to special relativity. And they're one of the things that let us disentangle what the mass and the radius is doing. So every photon that arrives from the star, basically, we record the energy channel it arrives in, and we put a timestamp on it, mapped to the clock of the pulsar's rotation. So it drops into a rotational phase bin and forms over time. Every photon that arrives is dropped into an energy and time phase bin. And we build up this thing called a pulse profile, which you see here, where the colors indicate the number of counts or photons that we have. Here you see essentially 2 full rotational cycles for this one, just for clarity. And you can see there's one rather bright peak and another one that's slightly dimmer. So this is just an example. So that is the data that is coming from NICER. Here are 2 examples. This is the one that you've just seen. What you're seeing in the top here is what we call the bolometric pulse profile. So now I'm summing up over all the energy channels. And again, you can see this very bright peak here and a slightly dimmer peak basically here. And this is one of our brightest sources. What you're seeing on the right-hand side is the kind of other end of the extreme. This is our dimmest source that we've tackled to date. It's a very interesting source for reasons that I'll come back to later. But you can see the kind of difference in the data quality. You can see the 2 pulses basically in the bolometric pulse profile. But when you actually look at the energy resolve spectrum, it is much harder to pick out by eye the fact that there are actually 2 pulses. Okay, so these are the kind of 2 extremes of data that we're working with. They take 1 or 2 megaseconds of observations in total, several weeks, to build these data sets up. And we do that over the course of 1 or 2 years, or even longer now. They're very stable sources, so you can build up data over a very, very long time quite safely to increase your pulse profile data set. Okay, so let's come on to the modeling side of things. I have my data. I now need to have a model that predicts what that should look like, basically with all of the parameters essentially that I think are relevant. And we're going to be doing Bayesian inference. So we're going to use that to do a likelihood calculation to estimate distributions of all of those parameters. So what sits basically in my model that can simulate and produce simulated pulse profiles? Well, all of the things that we've talked about, the relativistic ray tracing. So I have relativistic ray tracing model, which is something that we understand very well. I have to basically have some kind of atmospheric beaming model in there as well. Neutron stars have a thin atmosphere, perhaps of hydrogen, perhaps of helium, that will affect how the radiation comes out towards me. So I need to model that. We have interstellar absorption to contend with. So that'll be one of my parameters in my model that affects what we observe. As I simulate radiation coming towards me, of course, it's being detected by an instrument. So to compare with data, I also have to have a model of what the instrument is doing. And although NICER is, of course, perfect, our understanding of it is not necessarily so. And so there's some uncertainty, for example, in the effective area of the instrument at different energies. So this is also something that we include in the model to take account that uncertainty. We then also have to think about the hotspots, basically, that we have in here. So essentially, we have these hotspots on the surface. And if you go and talk to a pulsar astronomer and say, okay, what range of spot shapes, temperatures, sizes do I need to consider, basically in my modeling? They will say, well, this is an extremely, extremely challenging problem because they do not necessarily know this essentially a priori. So they might show you something like this, which is a return current simulation. So you then have to map return currents to temperature distributions, and we want to allow, the range of possibilities that the theorists consider to be an option. So we then, right now, what we do is we develop parameterized models of possible hotspot shapes. So the example that we use in my team's code, for example, we build possible shapes out of circles. So, for example, we can have simple circular hotspots as one possibility. Maybe we allow 2 on the surface of the star. They can have their own temperatures and sizes. We can have core and annulus regions, so we allow some kind of temperature gradients. We can allow the center to be a little bit offset, or we can even allow them to overlap to form shapes like crescents. So we build up these various possibilities informed and inspired by theory, but not yet directly connected to return current modeling. And then we have these broad parameterized models, and we use these. Okay, what else do we have to put in there? We have the distance of the star. That will actually set how bright things are. Maybe we know that up front, maybe we don't. The angle that we're looking at the star at, the inclination, will affect what we see. Again, maybe sometimes we know this, maybe sometimes we don't. Hotspot properties I've mentioned. And then we may have priors on some of these parameters. So sometimes these sources are also radio pulsars, and our radio pulsar colleagues can actually give us really good information, perhaps even sometimes on the mass in advance, and the distance and the inclination. We have to decide also on priors for, what do we consider a reasonable radius for the neutron star? And here we turn to our nuclear physics colleagues to ask them kind of what's a reasonable range of radii that we should be considering as priors in our models. So these are the kind of things that we're putting in to try and simulate something that looks like the data. Basically, we then come into this large-scale statistical sampling process, and we have a number of codes that are doing that. I'm going to talk about results from my group, which is coming from one particular code, which is available open source if anyone is interested in playing with it themselves. We rely typically on open source statistical samplers to survey across this huge parameter space and to do the Bayesian inference. We have cross-tested our relativistic ray tracing models really, really well. And we've also done parameter recovery simulations to verify that if we simulate data, can we actually recover what we put in? Basically, so there was a whole exercise done as well to try and cross-test our codes. What do you have falling out essentially at the end of the process? Well, as a result of this, essentially we have our data, we have our simulation model, large-scale statistical sampling, and at the end of it, we have posterior distributions on all of our model parameters. So that's the mass and the radius, which we want for the nuclear physics, and also the geometric properties as well. So kind of as a side benefit of the analysis, we produce essentially a surface map because we actually also infer the properties of these hot magnetic polar caps. And I actually think that's one of the coolest things that we do, in fact, even maybe a little bit more exciting than the mass and the radius. So I'm going to talk to you first of all about the surface maps. What I'm showing you here is the first surface map, essentially, that we published. So this is our first surface map. Maybe I can set that rotating. So this is for a star that is thousands of light years away, and it is the size of a small city. And we are in principle able to use relativity and X-ray data to make a map of the hotspots on it. And this is not an image. Basically, this is using other tools from timing and spectral analysis. And it kind of blows my mind that we're able to do this. So this was the surface map that we inferred for the first star that we looked at, which is this one that you've already seen with these very bright 2 peaks. This is a star where we don't know the mass ahead of time. Basically, it's not in a binary system. We have very little information about it. And what you can see here, essentially, is that we have, for all of the models that we looked at, this was our preferred model. One of the magnetic poles appears to be a kind of small spot, and the other one is this kind of slightly longer extended region. And that's already, a kind of fun thing to find, because you can see straight away, this is not a simple dipolar magnetic field. So all these lovely cartoons of neutron stars with, pretty straightforward, simple dipole magnetic fields, this is not what it is looking like down near the surface, as far as we can tell. Instead, it looks like the magnetic field has to be something much, much messier. Something more like this, perhaps with quadrupole components, perhaps with an offset dipole. And this kind of raises all kinds of interesting questions, because these are old neutron stars. They've been formed in a supernova. They've gone through a phase of accretion from a companion star, which may or may not still be there. It may have been completely destroyed by the accretion process. And that's actually spun it up to these millisecond periods that are so important. So the question is then, how did this magnetic field form such a weird structure? Has it been like this ever since the supernova? Maybe. Or did this form through the accretion process? Is that how it got so distorted? So this is now an interesting question for people working on pulsar evolution, to try and work out how this kind of magnetic field structure came about. So what I'm showing now is that the surface map on the right for the second star that we analyzed. This is the one with the kind of more ratty data set that I showed, but it's a fascinating star because we have a mass measurement for it. And we also know very well what kind of angle we're looking at it from, because it's a radio pulsar in a binary, and our radio pulsar colleagues were able to measure the mass. And it's actually the most massive neutron star that we know, well, we know the mass very well. So we were able to use the mass information already, and use that to supplement our analysis. And here is the surface map for this one. It seems a little bit simpler in terms of the magnetic pole shapes, as far as we can tell. But again, they're still not directly opposite each other. This is not a simple dipole magnetic field either. So basically, this is our side benefit, mapping the neutron star on the outside and being able to see something about the magnetic field structure. But I promised you internal mapping, so let me now show you what we measure for the mass and the radius for these two stars. So basically what you are seeing here are our inferred masses and radii from our first two results that we published. Down here for this double peak star, and up here for the one that had the higher mass. These are 68% and 95% credible regions coming from our analysis, compared to a whole bunch of models, mass radius relationships. So you can see these regions are still reasonably large at the moment. They're also quite similar in terms of the radius, despite the difference in mass, which we found quite interesting. And you can already see it looks like some of these regions, perhaps at very low radius, are a little bit disfavored by these measurements. But this was our first attempt at doing this with smallish data sets. And as we build up more data, these regions in principle should shrink. Now, what did we learn along the way of doing this? One thing that we learned, which probably with hindsight we should have known already, was the importance of background. When you see a pulse profile like this, it is not sitting on 0 counts here. It is sitting on a finite number of counts. So there is a component in the emission spectrum that is not varying as the star rotates. Now, that can come from astrophysical backgrounds and particle background. The space station is a very high particle environment, a lot of space weather, so it has a relatively high particle background that affects what we observe. So it could just be from there. However, an unpulsed component can also come from the spots. For example, if they overlap the rotational pole, or if you have extremely strong light bending because the neutron star is very compact. So what you really want to do ideally is have some proper idea of what's coming from the source and what's not, to try and separate these possibilities. And for a long time, that was very difficult with just NICER on its own, because estimating the background component for NICER has been quite hard. So what we actually do is we use data from other telescopes where it's easier to separate out source contribution from background contribution, and then we model that simultaneously and use that as an indirect way of constraining the background. And in fact, for this high mass star, in fact, it shifted the whole radius by about 1 kilometer when we included these background constraints. So that turned out to be incredibly important. So we now know that knowing the background is really important. So now let me come on to NICE's brightest target, which is the most recent one. Well, almost not quite the most recent one. We have one more weird one now, but this is the big one that we wanted to publish. This is the source that is NICE's brightest target. And you can ask, well, why didn't you do this one first? It has a known mass. It's in a binary. Our radio pulsar colleagues at the Parkes Pulsar Timing Array were able to get a really good mass for this one. We knew the mass to about plus or minus 3%. It's a 1.4 solar mass neutron star. It's your typical textbook neutron star mass. Here is the pulse profile. It's absolutely beautiful. Huge numbers of counts. Basically, slightly offset pulse shape, one big main pulse, and this kind of kink here, basically presumably from a second emitting region. The problem with this one is black holes, because in the field of view, basically of this star, of the telescope, when you look at this star, there is a bright active galactic nucleus, and we do not like black holes. It emits very brightly in the X-ray, and it actually contaminates what we observe for this star. So what NICE has to do is point a little bit off axis, basically in order, that kind of optimal pointing away from the source itself, in order to minimize the contamination that we're getting from this active galactic nucleus. It still contributes to what we observe, and it can be variable, but we were trying to offset that. So we had to understand how NICE behaved, basically when you point things slightly off axis as well. So basically this one took us a little while to get to, and then it proved, because the data were just so great, a very, very hard source to actually model. But we've now managed to do it. So basically, first of all, the surface map. We have quite complex surface temperature patterns emerging from this one. These are showing two different angles. This is looking along the equator of the star, and this is the angle we actually think we're looking at from the Earth. A kind of dual temperature region on one magnetic pole and a ring-like structure basically on the other one. Again, it's just not a simple antipodal dipole coming in there, so fitting this picture of complex magnetic fields. What about the radius? Well, these are the results that I showed you so far, and here is the mass prior, basically, that we took from our radio pulsar colleagues for this source before we started. So down essentially around basically 1.4 solar masses, basically falling into that region there. I'm going to just make one small update to the high mass star, because we now have 3.6 years of data. So that one's shifted a little bit. Tricky source essentially to get tighter constraints, basically, but this one is slowly evolving as well. Basically, and again, that will start to tighten over time as well. So let me now show you what we've managed to get essentially for our brightest source. This is the mass and the radius, basically, that we managed to report from the first data set. So this one, quite low radius, basically, in principle, compared to the other two, although, again, these are very, very broad regions. Basically, this is an interesting one, because this is not really the only way to probe the equation of state. Our gravitational wave colleagues are also making measurements of the neutron star equation of state. They're doing so in a different way. So they are looking at merging neutron stars. And of course, there's a very famous merging neutron star event, GW 170817, basically the first and brightest neutron star merger, essentially observed with LIGO scientific collaboration with LIGO Virgo together. And there's an electromagnetic counterpart, so you can be sure it's a neutron star merger. And basically what they're able to measure is the tidal deformability of those neutron stars as they spiral in towards each other and deform. The mass and the tidal deformability also depend on the equation of state. So they were able to get from the gravitational wave signal an estimate basically of the equation of state as well. And what they found essentially was quite a soft equation of state, basically from that event, which would imply a much lower radius. So the two NICE measurements that had come before were a little bit higher in terms of radius, consistent because our error bars are all quite large. But essentially they were tending towards rather softer things. Our latest measurement is very, very consistent with what the gravitational wave people are finding, which I guess is somewhat of a relief basically for all of us. Now, you may also be looking at this and saying, well, hang on a minute, this one down here does not look particularly consistent basically with your newest measurement. But do not worry, because we have also updated that one. When we did this analysis here, we didn't really have a full handle on the importance of background estimates. And so we did the analysis without having a background constraint in there. Now, once we'd done the second one and realized how important it could be, we actually reran that analysis with a background constraint from another telescope in there. Picture got complicated. It actually becomes a bimodal solution. We have two possible solutions for the mass radius with different magnetic field geometries, which is interesting. But one of them is the one that I'm showing here, which is extremely consistent, basically with the latest result that we've published as well. So there is at least a consistent solution. And so that I think right now is not a worry, but it's something that we have to confirm again with future larger data sets for that source. So far, what we have are a bunch of inferred masses and radii, but of course we want to do nuclear physics. So we then have to go back and do this next stage of analysis. So we basically have to take our mass radius measurements and we want to transfer them into an equation of state, or effectively to transfer our individual measurements into a mass radius relationship, basically taking into account possibilities for the dense matter. So this means the second phase of Bayesian inference. So we go and talk to our nuclear physics colleagues. We discuss with them possibilities for an equation of state model that can be parameterized in various different ways. We pick priors perhaps on those parameters. And then we do the second phase of Bayesian inference to infer a mass radius relationship. This has been a huge number of people are working on this. I can't show all of them in the talk, but I'm just going to give you one flavor from the analysis that we've been working on together with collaborators at the Technical University in Darmstadt. So for example, we picked a model where the outer part of the star is basically being driven by chiral effective field theory. So we have an equation of state that's consistent with chiral effective field theory. For the inner high density part of the star, we picked two different parameterizations, one based on polytropic models of the equation of state, which a lot of different people have been using also in the gravitational wave community, and another model where we're modeling things in terms of the speed of sound within the star, which has the benefit of getting rid of discontinuities in the equation of state. And part of the reason for doing that was just to try and understand how sensitive we were to model choices. But you can pick any equation of state model of, that you want at this point. So basically, when we do that, for example, if we take our current data, and I've picked this one down here that's consistent with the latest result, and I'm then going to put in an equation of state model. So this is just one example from a recent analysis in Rutherford et al. This is our prior on the equation of state, basically of all the prior parameters that we're taking. And you can see already that for this particular model, there's a preference essentially for radii around 12 or 13 kilometers. Okay, so we have essentially a preference coming from the model. It's not particularly due to physics. It's also due to the way that we've chosen our priors, but you also need to be aware of that. We then fold in our mass and radius, and we can fold in the gravitational wave results as well, and any other constraints that we want to put in there. When we do that for our current results, basically, and the current gravitational wave results, this is the inferred mass radius relationship that we end up with. Okay, so again, still favoring basically around 12 kilometers, basically partly driven by the priors, but now also partly informed by the data, and everything getting much narrower. So this is the process that we're now going through. You can see again these kind of very soft equations of state, kind of disfavored, and now these very stiff ones as well, but that also comes from the prior. And again, lots of different nuclear physicists working on taking this data and trying to understand now what it means for quark matter, for hyperons, and so on in the cores of neutron stars. So what comes next, basically, for NICER? First of all, well, in principle, there are 7 targets that are accessible to NICER. It's a relatively small telescope, so we need quite bright rotation-powered pulsars to get enough photons to enable us to do this kind of analysis. We need megaseconds of data and millions of photons to even be able to start analysis. So basically, we've got these 3 that we've published. There are 4 more still to come, some of which we have mass estimates for. And in fact, we have actually done another one and published it, but this one is weird. So I'm going to show you it, even though it is quite weird. We've called it a complex case, basically in the paper title. This is the pulse profile. So it has a very clear main peak, and it has this tiny little nub, basically, of a second peak in here. And we think that actually is why it's so difficult to model. It is in a binary, and there is a mass estimate for it from radio timing. And there's a kind of joint mass inclination prior for this source, but it's not a nice tight mass estimate, but we'll still take the information that we have. When we tried to do our standard procedure on this, we start with a very broad prior on radius because we want to keep it as general as possible. And we have this kind of very broad prior on the mass as well. What you're seeing here are a whole mess of posterior distributions. So let me walk you through what we're seeing here. This is one particular set of surface models, 3 hydrogen and 1 helium atmosphere in here. The first one that we tried was our normal broad radius prior. It started to come up in this direction, but it was very, very hard to get it to converge. The analysis was taking forever, really, really complicated. So in the end, we said, okay, well, maybe this one's just difficult to model. So at the very least, can we tell if it's consistent with the others? So we then went to the other extreme and said, okay, if we go back, for example, to this inferred equation of state that we have here, if we had taken that as our mass radius prior, basically, so that's saying the radius has to be somewhere kind of in this range, would we have got terrible, terrible answers when we tried to model this guy? So we put in basically a radius prior, which is shown here by the dot dash line. And we ran our analysis, and we can get something that looks quite like the data without a problem. Okay, so it is not inconsistent with that, which is great news. And we then tried some slightly broader priors. Again, it's all fine. There's nothing inconsistent in here, but it is very difficult to get a priori constraints. We're going to need either much, much better data to really see what is happening in here, or perhaps for this source, the geometry is just simply not favorable to the kind of analysis that we want to do. So this one's been a little bit frustrating. I wouldn't use this for dense matter studies, but at the very least, we can say it's not giving us inconsistent answers. What else do we want to work on? Well, I already said to our surface temperature models, they're an integral part of what we do. We have to allow all these different possibilities for the kind of shapes that might fit the return current distribution and the temperature distribution on the surface. It is quite possible that that is way too broad because it is not directly connected to magnetospheric models. What we would love to do is to have our parameters be things like the magnetic field and the magnetic field geometry, and have those determine from the start what those temperature distributions are. So we're now talking with the pulsar theorists about trying to make that part better and to exclude things that are simply unphysical. I'm pretty sure our current prior space includes configurations that would just never be physical. Perhaps they can never explain the radio emission, which also comes from the magnetic field. So this is somewhere I think we can do much, much better in terms of our modeling. Then we're thinking about other source types, because these rotation-powered millisecond pulsars are not the only kind of neutron stars with spots. And all we need are stars with spots. So there are a whole population of neutron stars which are accreting and have spots. So now basically these are neutron stars that are accreting material from a companion star, basically mostly via an accretion disk. That material is flowing in towards the surface of the star and settling onto it. Basically, and we have an awful lot of stars in that category. And again, fortuitously, the emission tends to be in the X-ray band. Okay, so we can use X-ray telescopes again to try and get at the surface emission. Why are they spotty? Well, 2 reasons. First of all, basically, you may have channeled accretion. So the magnetic field channels the accretion basically onto the magnetic poles of the star. So again, you have hot spots, and as the star rotates, you see pulsations. We've started to do some work on this. These stars rotate super fast, so in principle, they will be great to get all these nice special relativistic effects. Again, they're challenging. They can be variable. We've done some simulations now of what the kind of spot shape might be. You know, this is the kind of thing we're coming up with. It's not a circle for sure, so we have to think quite carefully about how we're going to describe that in our modeling. The accretion disk is also emitting in the X-ray, and we need to know what that is doing as well and to disentangle it in our modeling too. So that's a challenge to get those to work, but we're starting to make it work. We also have neutron stars where, as the material piles up on the surface, it can explode in a bright type 1 X-ray burst. And again, we can get spots forming on the surface. These ones are even more challenging. They are highly, highly variable. We do not know what makes the spots on the surface. It's thermonuclear flame spreading or thermonuclear hurricanes or convective patterns or something. But they're very bright and very interesting. The spot may be moving on these sources. So we've had to do a lot of work, unlike the nice sources where the spot is stable, to work out how on earth we're going to deal with the spot moving around as well. So this is something that we've been working on trying to take into account all of this uncertainty. We're starting to get constraints and working out the kind of computational cost of this analysis. But it looks like we'll be able to do something if we can get some better handle on the models. So I am coming towards the end of my time. So let me wrap up where we are. Basically, NICER is really unlocking a completely new technique for determining neutron star properties, basically using these high quality X-ray spectral timing data sets, relativistic ray tracing, and then a large amount of computer time basically to process these models. So far, we've measured the size of 3 neutron stars pretty well. We have more neutron stars basically to come, one of which seems to be a bit horrible, but hopefully 3 more that will be better. We're building up more data, and those regions will shrink as we get more and more photons. And as I said, the one thing that I love along with this is, in addition to getting dense matter information, we're also making these maps of these tiny, tiny stars, thousands of light years from Earth. And the thing I am absolutely the most proud of is that we've taken the nice emission patch and shown that it probably doesn't look like that. It probably looks an awful lot more like this with a slightly weird magnetic field structure. So I'm at 45 minutes, so I will stop there and take any questions.